So this video is on statistics or options for statistics in R. So I'm going to clear the environment first. A key thing to know about distributions, densities and such in R is just like maxima, the first few letters would determine the type of density we are going to, or the type of function that we are trying to evaluate. So in R, if the name of the density or if the name of the function starts with a D, it stands for the density. If it starts with a P, it stands for the cumulative distribution function. And if it starts with Q, it stands for quantile function. And if it starts with R, then it is random number generation. So since we're going to deal with random numbers, I'm going to set a seed so that whatever I do is replicated or reproduced in yours also when you run it. So I'm going to set a seed of 04142020. The first thing I'm going to do is I'm going to generate a sequence of numbers between -5 and 15. The length of that sequence would be 256. So -5 up to 15, the length is 256. Now what I'm going to do is I'm going to generate a density evaluated at all these values of x, and I'm going to generate a normal distribution function. So since this is a density, naturally we have to start with the letter D. So I'm going to put, not to confuse here, that D is a variable, but when I say start with the letter D, I mean D norm, which stands for density of a normal distribution. I'm going to have to evaluate the density at the given values of x, which would be those, and I'm going to say that the mean of the density is 8 and the standard deviation is 2. I'm going to plot this density. So for all the x values and the density that we just evaluated, I'm going to set type as L, and I'm going to give it a title. An X label, a Y label, line width of 2, and color 4. And I source that. And that is the density that I get, and as you can see, the mean is at 8, which is right over here, and the standard deviation is about 2. Now, the next step would be to generate random numbers from a distribution, and I'm going to pick a normal distribution again. Now, you can use other distributions such as binomial, Poisson, exponential, and so forth, and they all follow the same pattern. It's going to either start with D, P, Q, or R, but the name that follows, you've got to Google or look in the documentation to determine how the name is specified. For example, exponential distribution is EXP, gamma distribution would simply be gamma. So if you want the density of a gamma distribution, you would simply do D gamma. If you want the density of an exponential distribution, then you'd go D exponential, or excuse me, DEXP. If you want to generate random numbers from a gamma distribution, you'd simply do R gamma. So I'm going to create a variable, rand norm, which is going to contain random numbers generated from a normal distribution. So I'm going to type R norm. The length is 1024. The mean would be 8. And the standard deviation is 2. I'm going to visualize to see if this distribution is in fact normal. In other words, or if this sample is in fact a normal sample. In other words, if I get a histogram, it should have a bell-shaped curve. So I'm going to go for the hist function. The variable that I just created. Breaks is a parameter that is used by the hist function to determine the number of classes that you want in your data, or the number of bins. So typically for 1024, or for a sample of length 1024, breaks, it's about 20 or 30. You don't want too many breaks, you don't want too few, if you want to get a good picture. Going to specify a title. An X label. Y label, which should be the density. And going to type the parameter freq. If I specify false, it is going to have the density in the x-axis. If it is true, it will simply count the number of observations that belong to a specific interval, and it's going to put that count or frequency on the y-axis. So you can see that we have a bell-shaped curve, or a bell-shaped histogram clearly indicates that the sample that was generated and saved to the variable rand norm is in fact a normally distributed data with mean 8 and standard deviation 2. The next thing that I'm going to show is how to create a data frame. While lists are good data structures in R, in terms of handling data, and S for objects, which are classes, they are good to define functions and objects of higher variety, such as a test, which we'll talk about. Data frames are great at handling real data. In other words, data that we import from an Excel file, a CSV file, and so forth. You can directly import it as a data frame, and you can manipulate that data to perform analysis, but you can also create your own data frame, and that's what I'm going to do now. So I'm going to generate a sample, use the sample command. So what this means is I'm going to randomly select 128 observations from those two possibilities, yes or no, in the list, and with the option of true. True indicates that I'm going to do it with replacement. If it is false, then it will be without replacement, and if I don't replace yes and no, and if I want to select 128 of them, it is just not possible. For instance, if I did sample yes, no, and I specified 128, and I give replace as false, it is going to give me an error because it says can't take a sample larger than the population when replace is false. So here we need replication. So what I'm going to do next is I'm going to generate random numbers from a beta distribution. So naturally I'm going to start with the letter R, followed by the name, which is beta, and the length of the random numbers, or the list of random numbers that I'm going to generate, which would be 128. And a beta distribution has two parameters, alpha and beta. I'm going to specify the values as 1 and 3. Now it is time to create the data frame, so I'm going to create the variable df. Data frame, and I'm going to give two names, response and probability. So I'm going to save the variable x that I created and save it to response, the variable y that I created to probability, and mind you, probability and response are now columns of df. Can ignore that, my figure window is small. So when I type df, I get that, and you can see I have a bunch of yes and no's with probabilities. The first column is response, the second one is probability. I can access each of the columns simply by saying df $response, which gives me the list of all yes and no values. df $probability, that is going to give me the probability values that we saved. So we're going to perform a one sample test for mean. Just like the take inference object in Maxima, the statistical test objects in R follow a very standard pattern. In other words, they're all list type objects and they have the same or more or less the same set of variables defined within the list, or elements defined within the list. So I'm going to start with a Ttest. I'm going to save the test results to df.t. The command here is Ttest. The response variable cannot be used with a Ttest because Ttest is for continuous data, so I'm going to use probability. Mu is 0.5 and the alternative is greater. So if you recall that hypothesis testing requires a null value, which is our reference, the reference for the distribution, the null distribution, and the alternative is we either test if the data is greater than the null distribution, less than the null distribution, or it is not equal to the null distribution. So here the test that we are performing would be to determine or obtain a conclusion is the true mean greater than 0.5 based on the sample. And when I run that, I get df.t, and it gives me the test results, and the first value there is the test statistic, that is the degrees of freedom, that is the p-value, which is 1, implies we shouldn't reject the null, and the 95% confidence interval is right here, 0.205 all the way up to infinity, and the mean of x is 0.235. Obviously, an average of 0.2354 is not greater than 0.5, so clearly the p-value is 1. Now, I can get all the elements of the test object by doing ls df.t, and that is going to tell me everything about the test. The alternative that was used, the confidence interval that it's going to return, the standard error, the estimate of the mean, the statistic, the null value, and so forth. I can access every single element individually, just like I would do with any list. So df.t $p-value is going to give us the p-value of 1, which we had earlier. If I change that to statistic, that is going to give me the statistic of negative 14.772, which we had earlier. One of the most important things in data analysis is to subset the data, because we wouldn't want all data in general, we just want some, and we want to use that for the analysis and leave out the rest. So what I'm going to do now is I'm going to create 2 data frames. I'm going to subset from the original data frame that we created, df, and if the response is yes, I'm going to take all values and save it to df.y. In a similar manner, I'm going to take the original data frame df. If the response is no, I'm going to save it to the new data frame df.n. So df.y now would contain only response values of yes, and in a similar manner, if we type df.n, we have values corresponding to no only. So here we want to do a proportion test. And the question we want to answer is the proportion of yes responses less than the proportion of no responses? And to do that, we could use prop.test, and first we want to know the total number of observations in the data frame. So if I do dim, which stands for the dimension of the data frame df, so when I do dimension, I'm going to get the row and column of the data, the number of rows and the number of columns of the data frame. The data frame is like a table, so I'm going to have 128 rows and 2 columns corresponding to what I've used there in generating the data frame. Since I want only the number of rows, which would give me the total number of observations in the sample, I'm going to put 1, and that's going to pick the value 128 and save to the variable n. I want to count the number of observations in the response variable that are equal to yes. So what I'm going to do is I'm going to do some response equals yes. So what is that particular line doing? So if I take df $response, that is the first column of the data frame that we created. It has a whole bunch of yes values and no values. Now, if I add a logical statement, I get that. So the first observation and response is no, so I'm asking the question, is df $response equals yes? So obviously that's going to be false. The second should also be false. The third observation is yes, so it has to be true. So that part right there tests to see if each observation matches the condition that we provided. The condition here is that the response has to equal to yes. And logical values are treated as zeros and ones in R. So when I do sum of df $response equal to yes, it is going to add all the true values and give us the number of yeses in the sample. So when I run that, I get 61. So there are 61 yes values and the remaining 67 are no values. Now there is an easier way to find this. It's using the table function. If I did table df $response, I would get 61 yes values and 67 no values. I'm going to perform the test now. Proportion test is prop.test, and I am going to specify the number of yes responses, which is x. The sample size is n. The alternative is we are testing to see if the yes responses is less than the no responses. And from here, it seems as though the yes responses are in fact less than the no responses. But we want to know if it is statistically significant. So that's our test result. And there is the test statistic, the degrees of freedom, and the p-value. Based on the p-value, we can conclude that statistically, the yes responses, the number of yes responses, or the proportion of yes responses, is not less than the proportion of no responses. I have created a data file which is called temp.csv, and I'm going to read that data file in. So we can easily read the data file in R using the read.csv function. Now, R can read different types of data files. It can read CSV files, it can read Excel files, it can read shape files, and what say you, we've got a whole set of options in different packages, but the simplest one would be a text file or a CSV file. CSV stands for comma separated values. So in other words, the data, they are separated, or the observations are separated by commas in the file. So I'm going to create a new data frame, df.f, and I am going to read the file, which is temp.csv, and that is in my working directory. And there is no header, so I'm going to specify header equals false. And the separator, even though it is optional, it is always good to specify. Separator is comma because we have a comma separated value file, CSV. So when I run that, I get df dot f to be those values. Since there are no headers in the file, R would generate automatic headers, which is v1 and v2. If you specified a header, or if the headers were present in the data file, you can simply say header equals true, and those header names would be transferred over here in the place of v1 and v2. And from the data, you could see that there are a whole bunch of NA values, and I want to remove those NA values. And you could use the same strategy to remove other values. I'm just going for NA in this case. So, I'm going to create a variable x, and I'm going to save every observation in the first column, which is v1. Mind you, v1 is an automatically generated header name. If your file has a header, you should say header equals true, and whatever name you have there would automatically come in to R. Likewise, I am going to select the second column, df.f$v2. So I have the first column saved to list X, second column saved to list Y. And you can see I have NA values in list Y. Now before I perform another t-test, I want to remove these NA values. So I'm going to create a new list, yNew, and I'll explain what this means. So I am going to save values to the variable yNew, and what is it going to have? It will have all the values of y that are not NA values. How do we find that? Well, when we do is.NA of y, we get those. In other words, it is telling us the first 44 observations are not NA, and the last 7 observations are NA. So, is that true? If you look at Y, the first 44 are not NAs, and the last 8 of them, are NA values. So, which is why we have true, 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 true here, corresponding to NA, NA, NA down there. So, what am I doing? So, I am going to select from Y every single value that is not all of those options. So not false would mean true. So I'm going to pick a true value, which is 2.2. Well, not, which is given by the exclamation point, not of a true value, not true, means false. So if I want to pick a value, not in this case, but some argument, I could simply say y of true. It is picking all of those observations. In other words, if whatever we have inside is true, then it is going to keep that value. So by doing not is.NA of y, all of the false values here become true values, and the true values become false. So when I do y of not is dot na of y, I'm going to only pick the true indices from y. So you can see the first 44 had numbers is.na of y returned false, not is.na of y returned true. So technically when I take not is.na of y and select it from y, I need to get the first 44, and I did. So I successfully removed the na values. Now I want to do a right-tailed test in R, so I am going to do df.rtn t.test the x value and the y value. Now keep in mind, this is going to perform a two-tailed test. And I'm going to specify an alternative as greater. In other words, we want to know if the mean of x values is greater than the mean of y values. And it looks like it, in fact, it is not. So the mean of x is not greater than the mean of y. So let's see if that is the case. The mean of x is 0.2538. The mean of y is negative 0.5136. It is the mean of y greater than mean of x, so clearly it is not. But if I changed it to less here, we're going to test to see if the mean of x is less than, if the mean of y is less than the mean of x. In that case, the mean of y is negative 0.5163 and the mean of x is 0.2538. So even though the mean of y is less than the mean of x, it is not statistically significant. So and that would be a two-sample test. Didn't mean to type two-sided. And I'd like to do a two-sided test before I conclude. Two-sided, two-sample t-test. I'll call it df.2t. So again, it is t.test. And I'm going to go for the data frames that I created already, df.y and df.n. I want to test to see if the probabilities for the yes group in terms of the average and the probabilities of the y group are not different. In other words, they are pretty much statistically the same. So therefore, I'm going to use a mean of mu equals 0. So I get 0.5324. Now I'm going to show you something with the sample here. The sample function has an option called prob. It tells you with what probability you want to select the values. By default it is 0.5, 0.5. Now I'm going to do 0.1 and 0.9. So I'm going to have more of yes values and fewer yes values and more of no values. And if I run that now, I get a different answer. And if you did table of df $response, you can see I have more of no values and fewer yes values. The reason is because we have the probabilities change from 50-50 to 10-90, 10%, 90%. So 10% wise, 90% wise, or yeses and nos. So if I flip it and write it as 0.9 and 0.1, now I have more of yes values and fewer no values. So, as I mentioned, by default the sample function would select with a 50-50 probability, but there are cases when you want to have more than 50-50 chance, so we can change the probabilities on how we sample.